Okay, hello everyone. It's very nice to see you all. Today we're going to have the pleasure of hearing Andreas, who is going to tell us about gravity factorized. Andreas, take it away.
Hi guys. Yeah, as always, thanks for the opportunity to speak. I'm gonna talk a bit about a quite recent paper. I think it came out on Tuesday or Monday for you guys, I'm not sure. With the Luca, Iliesiu and Jorrit Kruthoff. It's about factorizing gravity. Before getting started, I also want to give a shout out to some earlier collaborators on similar topics. Thomas, Henri, Jorrit again, and Misha. Also, I want to stress that if you guys have any questions or not explaining anything very clearly, that you should feel free to stop me. I mean, I try to limit the number of slides, so I think we should have time for questions if you guys have them. Okay, I started with sketching the program for today. As you may notice, I sort of put the conclusions before the actual calculations, because I think it's sort of useful to have maybe an orientation of where we're going and what the lessons are going to be before I put you through some more math-oriented stuff. Okay, let's get started. So the problems we'll be trying to solve are related with wormholes in quantum gravity. Okay, so I don't think I need to convince anyone that it's important to understand the duality between black holes and quantum mechanics. Also, I probably don't need to say this, but as you'll know, there's been a lot of recent progress in that regards that's come from studying wormhole contributions both in Euclidean and Lorentzian signature, for example, reproduced to page curve and other stuff. So wormholes are important, but they've also introduced two puzzles, and I'd like to address those puzzles today based on the paper that we wrote. The first puzzle is the factorization puzzle. Now, as you know, in quantum gravity, or don't know, if I compute the product of two partition functions, I am introducing two boundaries, and I should sum over all geometries that end on those boundaries. Just like when I compute a correlator in quantum field theory, I sum over all Feynman diagrams that connect them. But in quantum gravity, this gives us a sort of a contradiction, because it means that the two boundary partition function is not the square of partition functions. That a priori would be fine, were it not for ADS-CFT, which says that we should have a dual, or we want a dual description that's one quantum mechanics system. And then, of course, the product of partition functions is just a product of partition functions. Well, we don't have this in quantum gravity naively, so that's a problem for the dictionary. What it means is that unless we do something special, what I will call simple models of gravity will always be dual to ensembles. And simple models include Einstein-Hilbert gravity and supergravity in any number of dimensions. Because something quite magical needs to happen for this problem not to exist.
Andreas,
it's not obvious, yeah.
And as here already, I mean, okay, for very simple models, two-dimensional, I would agree totally. But let's say you're in n equals 4 and you have type 2b, or you have supergravity. Even there, you think this is an ensemble? Because you say that supergravity in any number of dimensions is an ensemble.
Well, I would think that in supergravity, I could I could write up a wormhole. And the mere fact that I can do that, I think, suggests that there's a problem there. And I don't see within that theory what would cancel a wormhole.
Well, maybe these wormholes exist in some interacting pairs of...
Exist in somewhat?
In some interacting pairs of quantum theories, right? Not in n equals 4. In n equals 4, maybe you cannot find, in the supergravity dual of n equals 4, maybe you cannot find such wormhole solutions, right?
I'm not talking about solutions
not even
necessarily.
solutions.
I'm talking about configurations. So like in a path integral, we're not supposed to count solutions. We're supposed to count everything. I think and I think there are. You can always consider wormholes, whether they be solutions or not, and I don't see why they would not be there in general, unless something quite specific happens.
So for you, these wormholes are even off-cell. Okay.
Yeah, I don't really, for these purposes, I don't actually care if they're on-off or on-shell or on-shell, just that they're not zero. And in JT, they're off-shell. So in that sense, okay. The second problem, is quite related, is a discreteness problem. I think this was introduced in a paper by Maldacena, 2001. So the dual, the boundary dual in ADS-CFT has a discrete spectrum, but known tractable examples of simple theories of quantum gravity, like 3D pure gravity and Jacques-Yves Teitelbaum gravity, both have continuous spectra, which is a tension. It's clearly related to the previous statement, but I think it's sort of separate nonetheless. And this tension is experimentally, well, quote unquote, experimentally visible in non-self-averaging quantities, such as the late-time two-point function or spectral form factor, or matrix elements of Hawking radiation, namely their deviation from being thermal or maximally mixed. Okay, so the problem here is that simple gravity, or well, one way to say this is that simple gravity doesn't know about microstructure. It knows about the sort of coarse-grained features of a system, but not about any specifics of the system, which again is a tension with the dual theory. Okay, so now what do we want to do about this? Well, we believe, I think most people believe this, that the UV complete theories of quantum gravity and ADS, like string theory, do factorize, and that each of those is dual to one discrete quantum mechanical system, so that there's no problem, no real problem there. I think there's recent evidence for this by Lawrence Eberhard, who I think argued that certain string theory factorizes. So I think that raises the question, or raises the question what the fundamental difference is with the simple models that we just described. And I'd like to rephrase that question as asking, what is it that we've forgotten in those simple models that we should include to get a factorizing and discrete theory? So what we want to do today is identify the necessary new ingredients that the low energy effective field theory like JT gravity should have, such that it factorizes and such that it has a discrete spectrum. Okay. So to further motivate this and sort of show you guys where we're going, suppose that we start with some UV complete theory of quantum gravity, but one that has a low energy JT sector, so that we can use our favorite toy model of quantum gravity. But now, instead of making an approximation that gives us JT, let's imagine that we're super powerful somehow, and that we integrate out all the other fields in the path integral, except for the metric and the dilaton. And the only thing we do is we tune the temperatures such that the temperature is low, so that we would have originally thought we would have found pure JT gravity, but now we've done something more precise. And so what we find is JT gravity, but with all kinds of crazy, wacky deformations in the action. It's a bit the idea. So one expects to find local deformations, for example, some general dilaton potential. I actually haven't shown the JT gravity action yet here, but it will come if you're confused for the moment, sorry. But we also expect in general to find non-local deformations from integrating out those other fields. For example, you could get a bilocal contribution to the dilaton potential, or trilocal or whatever. Now, the idea is that in this thought experiment of integrating out the other fields except that metric and dilaton, that we've really made no approximation. And so if the original UV theory factorizes, it computes a certain partition function, which is just a number. That number remains the same whether or not I integrate out other fields. So that means that the low energy theory that I've obtained should still factorize. I'm getting feedback from somewhere. Thanks. Now, if what I've just said makes any sense at all.
I wanted to ask a question. Oh. This is why there was a feedback. Can you hear me?
Okay, sorry. Yeah.
Yeah. So usually the Wilsonian picture is that if you integrate a massive field, you get local terms that are kind of, they're really non-local, but you can expand them in inverse powers of this mass gap.
Okay.
You usually don't get non-local interaction from the UV. I mean, if you do something like integrate out some infrared modes, then you might get that. But if you just integrate out UV, you will not get non-local interaction. In other words, there has to be a mass scale at some stage that suppresses those interactions. I mean, I'm just trying to see what's new here that kind of contradicts that orthodox point of view.
Okay. Yeah, I don't really know what to say to that, but one thing I would say is that maybe I'm overselling the word UV. Okay. And I just mean like a complete theory that has a discrete spectrum, and then maybe, as you say, the important stuff doesn't necessarily come from very massive things. But I'm just imagining whatever complete theory I start with a discrete spectrum, if I zoom in on low enough energies, this should be like JT with some deformations.
I'm just wondering what specifically gives the non-local deformation, because those are normally things that you don't get. So I mean, I would say if you get those, then your process of integrating out implicitly did something to the infrared. You neglected some phenomenon in infrared that is summarized by this non-local term.
Yeah, I wanted to represent something in the infrared, I guess.
Yeah,
because it's essentially a low energy theory that we're describing.
Well, so usually the word low energy is a heuristic, but sometimes when you integrate out massive fields, you also implicitly neglect some low energy phenomena. And I'm just wondering if that's what's going on here.
Okay.
Because normally you don't get non-local interaction from integrating out massive things.
Okay.
So one way to see it, your bilocal term has no memory of the mass of the thing you're integrating out. There's no place to put the mass scale there.
Yeah.
Can I make a small comment
maybe let's
by
just
any chance? Or maybe I can
Sure.
make it at the end.
Go ahead.
Yeah,
Luca.
like you're right that in quantum field theories, non-localities are suppressed precisely by the ratio between the energy scale that we're working with to the mass scale. And when we're doing a perturbative expansion, for instance, if you want to find some scattering process in the theory and around some given saddle, those non-localities play no role because of the suppression. But here, when we're addressing the factorization puzzle, we're trying to compare contributions, if you want, around different saddles. One is the black hole saddle, or two copies of a black hole, and one is the wormhole saddle. So first of all, they have different topology, and second of all, the wormhole saddle is typically much more suppressed than the black hole saddle. So then the question is, while you're right that if I compute some scattering probability or something like that in a given saddle, that these non-localities are not important, our idea is that they probably become important when you want to compare the perturbative expansion around this leading saddle to whatever subleading saddle you have.
Yeah, I see that, but just to press it a little bit more, this Wilsonian idea of renormalization is true non-perturbatively. For example, you can just do it for lattice QCD. But it's a little bit subtle because it depends how precisely you integrate out massive mode. And there are circumstances where formally integrating out massive mode also implicitly does something to the infrared. So it kind of seems to me that what's supposed to be going on here.
I think I can summarize by saying that that we don't really precisely know what gives rise to these terms, but that we believe that they're there, and it would be well, given that the conclusions I'm going to give, I think it would be interesting to try to make more precise where those guys should come from.
Okay.
What you say sounds interesting, so thanks.
Yeah, I mean, let me say what my mental picture is, which is different microstates that are almost degenerate are different by something very, very complicated, like the operator that maps you between one to the other is something that knows about the full theory. So I think pretty much any approximation will kind of do no justice to that subtle difference between different microstates, but this is an infrared phenomenon. I mean, those things are almost degenerate. They're operators that map you from one to the other is very low energy, but also very complicated. It knows about the full theory. So I think pretty much any truncation will kind of not respect that difference. But anyway, I spoke too much, so maybe I'll let you talk. But
well, I think that sounds reasonable and interesting to me. I'd love to understand it better. But okay, thanks. Maybe I'll continue now.
Andreas, just a quick question here, because I see this formula. Is this like a generalization of Coleman's bilocal axiom in some sense? This is a bulk bilocal.
Yes. In some sense, yes.
So I should
I'll say something about that at the very end of the talk.
Okay, thanks.
Okay, where was I? Okay, so as I was saying, if any of the stuff I just said makes any sense, then that should mean that there should exist possibly non-local couplings or potentials for which dilaton gravity does factorize and has a discrete spectrum. Now, because UV complete theories are quite scarce, especially we think, then we only expect this to be true for quite specific values of these deformations. So what we did in the paper was that essentially we bootstrapped these local and non-local deformations by demanding that the theory factorizes and has discrete spectrum. It's of course not obvious that that has a solution, but we found one. And then, okay, we have an answer that we can interpret, and we can then ask where it comes from in the UV, as was already suggested. Well, again, UV between quotes, but you know what I mean now. I mean the full theory of the universe, whatever it may be. Okay, so that procedure turns out works. So let's give you the answers and then show you why. So explicitly, we find the following form for the local potential. It's a formula that's maybe not super interesting for you right now. Let me flash it anyway. And a formula for the bilocal potential. And all other higher order potentials or multi-local interactions should vanish. It's what you find. Now, the thing that I want you to keep from this formula is that the bilocal potential is in some sense universal, but the local potential depends on H0 or H0, and H0 is the Hamiltonian of the fixed dual quantum mechanics system. So we have local interactions that depend specifically on the microstructure of the theory, and then a universal non-local interaction. Now, the role of that universal non-local interaction, as we'll see, is essentially to cancel out contributions from wormholes. And we believe, well, based on the introduction I gave, that we would need non-local interactions in general in low energy field theories in order to cancel contributions from wormholes and avoid the factorization paradox. Because, yeah, like I said at the beginning, there will generally always be wormholes, so something must cancel them. And basically the only thing that can cancel a wormhole, we think, is a non-local interaction. An important point here is that the non-local interactions are really tiny. So they're like suppressed by e to the -2 S0, which is the difference in how important the wormhole is versus two disks in the gravitational path integral. So generally wormholes are not super important. So then generally the non-local interactions will also be super tiny and not that important. And that's what I mean by they do not affect your everyday observables. Okay, and the second comment is what I just told you, that the details of the binary couplings, like the Hamiltonian H0 or like J, I, JKL, and SYK, I'll call the microstructure of the theory, they translate to details of the local bulk couplings, as we saw. So that means that ADS-CFT is still one-to-one. One boundary theory maps to one bulk theory. And we can also, in that same context, interpret the ensemble average version as one-to-one. Like an ensemble of boundary theories maps to an ensemble of bulk theories, where one interprets quote-unquote simple JT gravity as an ensemble of more complete gravity theories, the more complete ones being the guys with these potentials turned on. Okay. Now, the local interactions, they are tiny too. They're also exponentially suppressed. This fact that these interactions are tiny is why oftentimes JT gravity, or more generally just simple gravity, is a good approximation. Like surely Einstein gravity is often a very good approximation, and even, well, Newton gravity. So okay, whatever we found had to be a tiny effect. The point is that these tiny local and non-local interactions, they can become important when we ask well, extreme questions. Extreme questions being like the very late time effect of applying a perturbation. So like the late time 2-point function. Or when we ask questions about the black hole interior. So as emphasized in another paper, I guess about a week ago, physics inside black holes is very sensitive to microstructure, and there these interactions will become important. Now, of course, this raises a question already alluded to. is what plays a role of these non-local interactions in the original UV complete theory. Okay, so this is one picture that we have for that. So the point is that in string theory, there should be some stringy excitations that look like semiclassical wormholes. And I don't mean necessarily saddles or anything, just something that looks like sort of a smooth geometry. And that is because string field theory is like patterning over all metrics and everything else. So just like the pattern of quantum gravity, it'll include all metrics and all fluctuations around it. But of course, string theory is much more than that. And we could imagine that there could be stringy fluctuations that in some sense connect faraway regions of space-time, but that are by no means close to looking like a semiclassical geometry. So we can call these like a stringy non-geometric wormholes or something. So the point I'm trying to make is that although string theory factorizes, well, let's assume it doesn't factorize in an obvious way, because even there we have wormholes and something that needs to cancel it. And we believe that there are these non-geometric connections, which I drew here as some blue stringy thing. And so this thing, we believe in the low energy effective field theory would become like a non-local interaction. That's a speculation, of course, and it would be interesting to understand this in detail. But that it seems like we're still pretty far from that. It would require first understanding how even to make like a quote-unquote semiclassical wormholes in string theory.
Can I ask a quick question? It's unrelated to what we do in the morning, just at the moment, but do you know what this bilocal interaction look like in the matrix model language that's dual to JT gravity?
Yeah, I do.
Okay. Yeah, if you're going to talk about that.
Well,
yeah,
I'm not sure if I'm going to talk about it, but maybe I'm saying something about it at the end of the talk, and maybe we can come back to that at that point. Okay. But it's certainly in the paper if you're interested.
Okay, perfect.
But we do know what it looks like. Thanks. Okay, and well, similarly, like some local non-geometric stringy stuff we imagine gives like the local deformations. Okay, so that's what we believe the picture is. And, now let's try to derive this and make it precise. So what I want to do is explain how the results on this slide, these formulas for the local interactions, can be derived. So what we'll do is we consider deformed JT gravity. So here is the JT gravity action that I promised you guys. And the deformation can be like some generic non-local potential. Now let's expand this this non-local potential in like a basis of functions OG, which have a geometric meaning that also come with some expansion coefficients that I'll call Z brane, which also will have a meaning. This is just rewriting a generic potential in some way. Now, it's quite hot. It's a bit hot. Like the best way to deal with stuff like this, I feel, like deformations around GT gravity and what people have done with it in the past, is to take x of I deformation and expand out that exponential, and then compute each term in this series. And that gives you geometric intuition for what's happening in some sense. Okay, so let's do that. We have this I deformed over here, plus non-local terms that I suppressed because I wanted more than one formula on a slide. So if we write out this exponential, like e to the x is 1 plus x squared over 2, etc., then we get a whole series like this, with some e to the s naught suppression for all the terms. So what this is doing is this is inserting some stuff in the undeformed JT gravity path integral. So this each of these terms is like inserting an operator in the JT gravity path integral, like this guy, for example. And it turns out that the geometric interpretation is that each of these basic functions OG, it corresponds with inserting an extra geodesic boundary of length b in the JT gravity path integral. Okay, so this is the dictionary between a function and an extra geodesic boundary. Now, there's different ways to appreciate this formula. One is via the matrix integral, but I won't go into that that much. I think for today, I want to keep it more gravitational. And I think it suffices for you intuitively to note that geodesic boundaries are analytic continuations of defects or like kinks, where B is taking the opening angle of the conical deficit to imaginary values. And for defects, there is a well-known dictionary, like a conical deficit with opening angle alpha becomes this operator right here in JT gravity. You can see this because this guy will add like 2 pi minus alpha times phi times delta of x to the JT gravity action, basically. And then if we integrate out the dilaton, this will localize on r plus 2 equals 2 pi minus alpha up to some constants times delta of x. So this introduces like indeed like a conical deficit in the geometry. And a similar argument can be made for the geodesics, but I thought I'd present it here via the defects, which are a bit more well known. Okay. So now the deformations that we had on the previous slides are like integrals of these OG guys with the expansion coefficients that we had earlier. And now in this case, we want to interpret the expansion coefficients, or we're led to interpret those expansion coefficients really as wave functions that live on the geodesic boundaries. So we'll denote the geodesic boundary with a wave function z brane as this blue boundary. Can be thought of as Thomson as smearing the boundary conditions. But crucially, because we started out with non-local deformations, we'll also end up allowing for multi-boundary connected wave function components. For example, as you guys see here, we have a contribution that consists of 2 geodesic boundaries with a wave function that links these guys. So this will draw like this. So we have 2 boundaries and they're connected by a wave function. And these are these connected wave functions, or these different geodesic boundaries connected via some mutually smeared boundary conditions. These are the correlated branes that we talk about in the paper. We call them branes because there's an exponential of these guys being exerted in the JT path integral, and just like D branes and string theory are an exponential of boundaries. Okay, in summary, the most general sensible that we think deformation of JT gravity is equivalent to considering JT gravity with correlated branes with generic wave functions z brane of n entries. So in this new picture where we've expanded out the action, the partition function of JT gravity with correlated branes will get all kinds of wacky contributions. I shown a few here. We still have like the original genus expansion that we always had, so wormholes ending on disk, etc. But now we also have these extra brane boundaries. We can have multiple of those guys, and they can be correlated. So they can be 2 by 2 correlated, or we can have a connected 3-point function, etc. And one other less important ingredient is that non-local interactions can also connect to closed universes. And by closed, I mean guys that we previously thought were disconnected and disconnected from the asymptotic boundary. Okay. Now, the claim that I made earlier is that with these specific values for the brane correlators or dilaton potentials, that our theory will factorize and have a discrete spectrum, where the spectrum is given by the eigenvalues of this matrix H0. Moreover, it turns out that the computation of the partition function collapses completely to only these two geometries. So we only have the disk and the brane 1-point function, which is a lot simpler than all the mess I had going on here. So there's some massive cancellations in this sum. So to emphasize the point again, all geometries with any kind of wormholes involved will cancel out, and all that remains in this theory is the disk and the brane 1-point function, which is what Schenker, Sanford, Saad, and Yao in permutations called the half-wormhole. So the main difference with their work is that in our case, this is actually exact. Like the sum of these guys gives precisely the partition function, whereas they were thinking in terms of leading order. So we have checked that JT with these deformations exactly reduces to these terms, also non-perturbatively using the matrix integral. And I'll say a few words about that at the end, and feel free to ask me whatever. But we'll focus mostly today on the all-order genus expansion and why that happens, because I want to give you guys rather geometric intuition today than matrix integral intuition. Okay, so let's prove that this is true now. First, I want to prove to you guys that this equation makes sense. That if I add these two geometries, that I get a partition function with a discrete spectrum. And then later, I'll explain why all wormholes cancel. So, okay, the disk we know how to compute since 4 years or 5 years. So the only thing we need to do is compute the half-wormhole. And the half-wormhole we compute by this diagram. So we have a trumpet ending on a geodesic boundary, B, and then a wave function on the geodesic boundary. And we want to do this integral. And the wave function we use is this guy. Now notice that these two terms that we have here are sort of similar. Both of them feature essentially this cos. So when it comes to integrating over B, we really need to do only one integral, namely this type of integral. The trumpet partition function is well known. It's like this exponential with some prefactor. And now this is just an ordinary Gaussian integral and gives e to the minus beta e. So if I compute integral the z trumpet with this wave function, the first term I can write as sum over I 2 over b cos b ei to the 1/2, with ei being the eigenvalues of h0. I do this integral, then this guy gives me trace e to the minus beta h0. The other term, this ends up giving me e to the minus beta e. I'm integrating this with the genus 0 spectral density, or the disk spectral density. So this guy just gives me z disk. And in that sense, we find that the half-wormhole is this discrete partition function minus the disk partition function. So if we add to that the disk, then indeed we find that this equation is satisfied.
Andreas, can I ask something here?
Of course.
I mean, in some sense, you chose these Z-branes so that they do what you want, right? That they cancel essentially the other contribution. There's no other independent argument why Z-branes should be that. I'm trying to see if you have another physical argument. So essentially, you chose it so that it does the job that you want to do. Okay.
Yes, indeed. Like I said somewhere along the talk, which maybe I didn't make super clear, we want to sort of bootstrap these correlators such that they give us a factorization and discreteness. Let me maybe emphasize though that this answer is quite interesting in the sense, or it has some interesting features, namely that these guys, these two terms, they're like much closer together than they're like rather similar, more similar than you would think, because H naught, the eigenvalues of H naught will be approximately distributed as rho naught of E. So these guys are quite similar, and the differences are rather subtle. It'll be okay. That was just what I wanted to add. Okay, now I think I really want to come to the heart of the matter, as the most non-trivial part, which is to prove that this bilocal deformation cancels all wormholes. Okay, so the workhorse formula is basically this guy, and I'll show in the next slide that this is the next few slides that this equality will end up implying that not only the genus 0 wormhole is cancelled, but all wormholes are cancelled. So if you write this out explicitly in terms of formula, this is the wormhole. And here I have like two trumpets with a wave function that links them. That's a wave function. So if I need this equality to be 0, suppose I want this equality to be 0, the only way I can do this is I put Z brane equals to minus Dirac delta of B1 minus B2 divided by B1. Because in that case, this second integral reduces to integral dBB, C trumpet, which is precisely how Seichanger-Sanford computed the wormhole. Okay. Now, I want to prove to you that this deformation is a solution to the factorization puzzle to all orders in the genus expansion. So let's start with making the argument in case we have two boundaries. The key point really is that we can group together geometries in a funny way. And we'll group them together by sort of assembling them in terms of amplitudes that have the same internal geometry, sigma, but that have like different things going on their legs. And what happens is that we have like geometries where on those legs you can either have or not have a Z-brane two-point function introduced. And you can convince yourself that the whole expansion, if you write it up, organizes like this. Now, the point here is that it doesn't really matter anymore what's going on in sigma. Because now if we insert in this guy Z brane of B1, B2, and glue it together by inserting this guy, then we find that this amplitude is basically -1 times this first amplitude. The second amplitude also just gives -1 times the first amplitude. And this last amplitude gives -1 squared, also known as 1 times the first amplitude. So the sum of these guys is indeed 0. And the key technical point that saves us here is, I think we all feel that factorization in gravity is sort of a difficult problem. And the difficulties arise because of the large diff invariance, or the mapping class group in 2 dimensions. But the reason that factorization works here on a technical level is because, well, the mapping class group sort of acts simple on the legs. So gluing on the legs is still simple, whereas gluing in the bulk sigma can be hard. But we don't really care about the bulk sigma here to make the argument. That's the key. That's why things are simple. Rather fortunate. Okay, so this argument extends to multi-binary correlators too. Yeah, I don't think I need to explain this in too much detail. Basically, here you have like you have k times the z brane correlator, so this gives like -1 to the k times the origin times the amplitude where there's no brane correlators inserted. Now then this amplitude, which can be super complicated, and we need to sum over sigma, a whole mess. But this guy, the sum that comes out is just 0. So all these things cancel. And notice in particular the case n equals 1, which can be drawn like this. Okay, maybe this is a bit overkill, but in particular, this case means that also all, well, handles on the original disk will cancel. So literally all wormholes that were there are now gone in the original JT gravity. And the only exception to these enormous cancellations are the genus 0 disk and the disk with a brane 1-point function, because those guys don't have any geodesics between that, like that are homotopic to the asymptotic boundary on which I can insert these brane 2-point functions. Okay, so in summary, I'm just stating the facts again. So when we include this exponential brane 2-point functions in JT gravity, all wormhole geometries cancel to all orders in e to the minus s naught, and only the disk and the half-wormhole remain. And then the half-wormhole can be tuned to give a discrete spectrum. And we've checked in the matrix integral that the local and bilocal deformation that we have, if we put them through the matrix integral machinery, they also end up giving the discrete answer. I'll explain that briefly in the last couple of slides, which is part of this last section called comments and results, which contains also a little bit of a repetition, but I think some messages are worth saying twice. Okay, so one message is that though all wormholes have cancelled, they're still encoded in the statistics of the brane 1-point function or half-wormhole. And in particular, you can convince yourself with the formulas that are in the paper that upon ensemble averaging over H0 again, with the original measure for the JT matrix integral, that you recover the whole genus expansion. And that, of course, needs to be true, because if we want this guy to resemble one draw of the ensemble, then it had better been that the ensemble average reproduces, well, JT gravity dual to the ensemble. Okay, so what's important here is that the amplitudes on the right are suppressed by powers of e to the s naught, because wormholes are always suppressed, well, generally suppressed. So that means that for normal or simple observables, that the contributions of all of the half wormholes will be suppressed, just like the contributions of the wormholes in the origin theory were suppressed. It also means that for self-averaging observables, that the contributions due to half-wormholes in the UV complete gravity, or maybe UV is kind of the, but okay, in the complete gravity, they will emulate the contributions of wormholes in simple gravity, or JT gravity as an ensemble. So, and that's why simple gravity is often a good approximation, even for exotic observables, as long as they're self-averaging. For example, if we compute a page curve, about which I'll also say a few more words next couple of slides. They know that the more interesting class of observables that we should be considering in this new theory are non-self-averaging observables. Examples of this include the very late time matter correlators, or spectral form factor, and matrix elements of Hawking radiation. More generally, just anything that, in some sense, probes the interior of black holes. Again, here pointing out the recent paper by Harry and Lin. Now, for these observables, the half-wormholes, well, because they're by definition not self-averaging, for these observables, the half-wormholes give very different results than simple gravity or smooth gravity, whatever you want to call it. So, in that sense, simple gravity does not suffice to understand these things, and it's not suffice to understand the black hole interior. But I think one message that I want to give is that if you take simple gravity, but we soup it up with these non-local interactions, as we've done, that may suffice. So maybe we don't need to have like full control of string theory. Maybe we only need to understand how these non-local interactions appear in more realistic, higher dimensional, low energy theories of gravity to understand what's going on in these crazy examples. In principle, it should be possible to compute the matrix elements of Hawking radiation, for example, in such theories. I think it's pretty exciting prospect. And I think we also made already some progress towards that in a paper with Misha that I want to emphasize a bit here. Okay, this is a repeat, namely that it's crucial in the story to have non-local interactions. And we expect those to be there in any low energy effective field theory if it's like an accurate representation of the full thing, namely it factorizes and has a discrete spectrum. But again, the couplings, the non-local interactions and the local interactions are small, so it would be very easy to overlook, and they wouldn't have dramatic effects on normal observables. Okay, then another point sort of makes contact with a question that was asked earlier. Like if we can see this as an example of the Coleman-Giddings-Strominger thing, I think the answer is yes. So whenever what Coleman-Giddings and Strominger or subsets said was that essentially, or one of the things they said was that essentially all non-local interactions can be viewed as local interactions, but with random coupling constants. I think what I want to emphasize here, though, is that not all non-local interactions can be interpreted as wormholes. So not all random couplings can be interpreted as wormholes. Some non-local interactions will look like wormholes, but those, it appears, need to be very specific. Like clearly, not every interactions that we turn on between distant regions will look like something I can smoothly travel through as an observer. And there will also be non-local interactions that non-local interactions that we don't really can make geometric sense of. Yeah. I think this is a bit funny though, like we're describing the bulk theory with fixed couplings. And in some sense, we can see that theory as a theory with random bulk couplings. though they're not really random, it's just a way to encode the fact that it's non-local interactions. Still, in some sense, you can kill an ensemble by using an ensemble. A point of clarification, maybe. So this brane two-point function is quite similar if you guys read the papers of Sachenker, Yao, and Stanford, to what I call the linked half-wormhole, or the two-boundary component of the baby universe wave function. But there's one difference, though, that's important, namely that we put this guy in the exponential, so it's a deformation of the action. And the fact that it's an exponential is really key to resolve factorization to all orders in the genus expansion. Like in these equalities, it's very important that we can insert these two-point functions anywhere. And for that, you need it to be in the exponential. Okay, penultimate comment. We can also try to include matter in this, and we made some attempts to that in the paper, so I don't think it's a complete story yet. So one can argue that if we would include bulk matter on top of ordinary JT gravity, like say some free field or something, let's say we have a complete set of boundary states for that matter, like some Carty states, whatever, column B, then factorization, the demand of factorization will end up fixing the brane two-point function to this guy. This will glue like the Carty states, and this will glue the geometries, basically, so to cancel the original wormholes. So it's important that the states here are orthogonal and form a basis. Could also be a Kronecker delta. Now the one-point function, or the half-wormhole, and well, more generally all brane correlators, they will have matter particles ending on them, not only geometries. And this is important for observables like the page curve, because it means that these half-wormholes on which particles can end will emulate, upon averaging, wormholes with particles traveling around them, and those particles were needed to get a cell in the page curve calculation, which therefore we believe remains trustworthy even in this factorized and discretized theory, precisely because the page curve is self-averaging, so we can use this property. Okay, finally, a few words about the matrix integral. So, as you may or may not know, non-perturbatively, undeformed JT gravity is a matrix integral. Schenker Stanford proved this. The potential here is like one-on-one with rho zero. Okay. Now, what we show in the paper is that our local and bilocal deformations, so we add some X of operators here that come from what we inserted in the JT pattern. This deforms the matrix integral to this. So the origin of the Q I'll come to later on the next slide. This is the second to last slide, by the way. Let's see, I'm going a bit over time. Okay, the form of the action that we find can be found in the paper. But the important point is that because of this Q to infinity limits that we're forced to take, and that we derive that we need to take, the integrals over eigenvalues localize on the stationary points of this quote-unquote action. And this should be contrasted with the original matrix integral, where there's no such, well, there's a large L in front of the action, but nothing that's really pushing a saddle for the individual eigenvalues. There's only a saddle for the collective fields rho, because then there's also an L prefactor here. Here we have a Q in front of the entire action, and it becomes exactly infinite, not just large. So this means that the random eigenvalues are precisely fixed on the eigenvalues of H0. So they're frozen, so to say, to the energy spectrum of H naught. And there's actually a paper we cite in our paper, a math paper that did something like this before, like considered a matrix integral with a large prefactor and found that the eigenvalues localize. So that was pretty fun to link with. But anyway, the matrix integral essentially reduces to this guy a bunch of delta functions. Well, there's just another way to write localization. It's a bit stupid, maybe. Oh. Okay, now the point is that in this ensemble where the eigenvalues are fixed, one sort of trivially recovers the same answers that we found in the gravity calculation, namely the partition function is this guy. And so we know that this corresponds to these two geometries. So this remains true exactly. Finally, the parameter Q, it comes from a renormalization of the brane correlators, something I was a bit quiet about up until now. Namely that in gravity, when I compute, when I wrote stuff like this, we do not have stuff like this. Those are geometries that do not exist in gravity. They are cylinders between geodesics, and those are the general surfaces. Within the matrix integral, they are there. And therefore, you need to basically renormalize the brane correlators. And we explain that in a bit more detail in the paper. I think it's pretty obvious that what you end up doing is solving this Dyson equation for a new propagator. This would be the matrix integral propagator, which does have degenerate surfaces, and this would be the gravity propagator. And let's say the gravity propagator is delta of B1 minus B2 over B1. And the matrix integral propagator, let's assume it's like a Q times that guy. And there's a minus sign here. Okay. Now this the general surface just equals all the b's on the left and right. So the sum on the right becomes equal to geometric series q plus q squared, etc. Well, okay, minus q plus q squared. So this guy equals 1 over 1 minus q minus 1. So this equals minus q over 1 minus q, and we need this times this delta function. And we need this to be equal to the left-hand side. And the way to do that, the only solution is q is infinite. So that's where this q is coming from, because the operators we'll be putting in the matrix integral have a large q prefactor due to this normalization. Okay, for more details, see the paper. Thank you all for your attention. That was it.
Okay, thank you, Andreas. Questions? I have kind of a silly question. In the brane 1 point function, the matrix H naught appears like a square root inside of a cosine. My question, is there any problem if H naught is not possibly definite?
There's not. Yeah, we thought about this. I don't think we wrote something about it in the paper, probably. But you might think that's like it's a problem to continue that formula to negative H, but it's secretly not. And the reason is that the cosine, the complex cosine is like cosine of z only has powers of z squared. So it's actually secretly an analytic function of H naught when you compute it to continue to negative values. Whereas, for example, if it would be sine of H naught to the 1/2, that would have like powers H naught to the 1/2, etc. So there's no discontinuity in taking this cosine and going to negative energies. You can also just put it in Mathematica or something.
I see. That's good.
It's not an. I don't think it's a live question. Or, yeah.
Okay, thanks.
Well, thank you.
So I have a question, just a kind of general question. So I guess if we assume that this picture is going to work in general, I mean, it seems to place some constraints on the non-perturbative physics based on the semiclassical picture. So some kind of precise requirement that you're able to get these cancellations. I'm just wondering if I think there's some general kind of, if we try to apply this to a more general theory, is there something like not totally specific to each theory that we could say? It would be interesting if there was sort of a general constraint or something that you could make on non-perturbative contributions. It reminds me a little bit of like when you have perturbation theory and you have these divergences in perturbation theory, and then you in order to actually have sensible answers, you need non-perturbative contributions to do very specific things and divergences. I mean, not that this
does sound similar. Yeah, I don't know. I don't have a very precise answer, but I think that I think some aspects of this should generalize to like maybe even more so I don't know quite what to make about the non-local interactions, but the picture with the brane seems like the easiest to generalize in some sense. You could sort of imagine if you have like a higher, I think we wrote something about this in the discussion too. Like if you have a higher dimensional bulk or higher dimensional boundary, you can still put a brane that like caps off that boundary. So I don't know if you have this. I can draw a higher dimension, of course, but let's say this wiggly guy is the brane. And then here's some more general surface, whatever. And then we have times some sphere or something. I think you could still imagine doing something like this, perhaps, and having that cancel. For example, if we imagine like a wormhole in higher dimensions coming from something like this times Sn, then we could imagine that it could be cancelled by these then higher dimensional brane type objects. But I don't know how. It would have to be. That would have to be made precise, and it would be also interesting to map that in some way to, I guess, determine the action or something. Like here we had this duality between either having branes or deformations in the action. So it would be cool if something like that could be done more in general. But it seems like the branes would be the easiest way to generalize. If that helps.
Thanks.
Any other questions for Andrea? Okay, let's thank him one more time. And let's stop the